A very warm welcome. So we are Group 13 and we are excited to present our engineering programming project for KNJ2332, which is titled AI Decision Support Tool for Material Selection. We specifically chose it for the design of a heavy-duty conveyor belt roller bracket with a focus on Sustainable Development Goal 9, which is SDG 9. Now, before we dive into the content of the presentation, I would like to introduce our team members. My name is Ted Geoffrey, the group leader. I'll be joining me are Rowell Hilson Untan, Azrik Aifan, Devian Dickinson, and Marcel Masad. On to the next slide, which is the table of content. To provide a clear roadmap of our presentation today, we have organized our work into 6 key areas. First, we have the problem statement and the link to SDG 9. Moving on, we will discuss our material selection process. Next, we'll discuss our program design, which includes our algorithm and flowchart. Next is the MATLAB demonstration, or the result of the MATLAB code that the AI has produced. And last but not least, the conclusion to our presentation and to our assignment.
Before selecting the best material, we first need to understand the engineering problem. The component chosen for this project is a heavy-duty conveyor belt roller bracket, which is widely used in industrial material handling system. The main challenge is that the bracket must withstand continuous and heavy mechanical loads, while remaining as lightweight as possible. A lighter component reduces the overall energy consumption of the conveyor motor and improves operational efficiency. The project is aligned with Sustainable Development Goal 9, Industry, Innovation, and Infrastructure. SDG9 promotes the development of resilient infrastructure and sustainable utilization through innovation. Traditionally, material selection is often based mainly on cost, which can result in poor durability, corrosion issues, and increased environmental impact. To address this, our project develops a MATLAB-based AI decision support tool that evaluates material based upon multiple criteria, including cost, weight, mechanical performance, and sustainability. The objective is to identify the most suitable material that provides the best balance between engineering requirements and sustainable development goals.
So these are the materials that have been selected by our group, and the first one is the structural steel, which is has the lowest economic cost among all of the 3 materials, around 3.5 ringgit per kilogram. The con of this material is it has high density, which is 7,850 kilogram per meter cube, and low sustainability score, which is 4. And then the second material is titanium grade 5. The pro of this material is exceptional strength to weight ratio, which is around 4,430 kilogram per meter cube, and high sustainability score, which is around 8. The con for this material is it is very expensive, which costs around 160 ringgit per kilogram. The last material is EcoBrass. The pro of this material is lead-free, naturally corrosion resistant, and it has high sustainability score, which is 7. And the con of this material, it is the heaviest material evaluated at 8,250 kilogram per meter cube, and the cost is moderate compared to the other 2 materials earlier.
Now, for the algorithm. Our algorithm executes a structured 5-step optimization process. First, we select 3 materials that represent extreme engineering profile to test our system: structural steel, titanium grade 5, and EcoBrass. Second, we establish our fixed design constraints. For this specific roller bracket, the volume is locked at exactly 0.001 cubic meters. Third, the algorithm computes physical mass and resulting material cost. Fourth, because mass, cost, and sustainability use completely different units, our algorithm performs a crucial step: normalization. For weight and cost, lower is better, while for sustainability, higher is better. Fifth, the system runs our weighting formula, where we allocate a dominant 40% weight to sustainability, ensuring our decision-making explicitly prioritizing eco-friendly infrastructure without ignoring realistic economy boundaries. For cost and weight, the respective weightages are 35% and 25%. Sixth, the AI evaluates the highest scoring index, then chooses the best material with the highest score and gives its reasoning. It generates three comparative bar graphs for weight, cost, and sustainability before reaching the end of the program. To use this strategy programmatically, we converted the logic into clean pseudocode. The program initializes the data matrices and uses a sequential loop to execute engineering calculations for all materials. It then determines the mathematical minimums and maximums across the dataset to execute the normalization arrays. After evaluating the weighted score formula, the script utilizes an array indexing function to identify the highest performing material. It concludes by using automated conditional branches to dynamically retrieve and print the exact technical justification for winning material profile. Now, finally, our system process flow is visualized in this flowchart. We fully converted our algorithm to a flowchart so that it is easier to visualize the flow of the system.
Now we're moving on to the MATLAB result. First, if you look at the screen, this is the output generated by our code. It doesn't just show random numbers, it systematically processes the physical density, market price, and sustainability scores of our three candidates. You can clearly see how the program organizes these complex engineering parameters into a clean, readable, and actionable format. Now, moving on to the most important part, which is the AI logic. Based on the 40, 35, and 25 weighting criteria that we defined, our algorithm produced this dynamic justification, which it identified structural steel as the winning material. The AI concluded that despite having a lower sustainability score, the massive economic advantage of steel makes it the most viable choice for large-scale infrastructure projects under SDG 9. This proves our tool can look past idealistic choices to prioritize real-world financial feasibility. Now, last but not least, we visualize the performance using these bar graphs generated by our MATLAB code. On the weight chart, you can clearly see titanium is the lightest, which is great for motor energy efficiency. On the cost chart, or the pricing, steel is the clear winner for budget-constrained projects. And last but not least, on the sustainability chart, you can see how titanium and eco-brass leads the environmental performance. So our tool effectively balances these three conflicting factors into a single objective score, preventing human bias from influencing the decision.
In conclusion, this project successfully demonstrated the application of MATLAB as a sophisticated multi-criteria decision support tool. By automating the material selection process, we have effectively removed human bias, replacing subjective estimation with strict, normalized mathematical weighting. Our analysis proved that in the context of SDG 9, selecting the optimal material requires a delicate balance between technical performance and economic viability. While innovative materials like titanium and eco-brass offer significant sustainability advantages, our AI algorithm identified that structural steel remains as the most mathematically sound choice for large-scale, heavy-duty industrial infrastructure. This project highlights the critical role of engineering programming in transforming complex, conflicting data into clear, actionable decisions for the future of sustainable industry.
So that is for our group. We concluded our presentation here. Thank you for watching and listening.